Okay, let me share my screen. Ohmmeter. Okay, this is the last subtopic in this chapter. Ohmmeter. The purpose of an ohmmeter is to measure resistance. Resistance reading is indicated through a mechanical meter movement which operates on electric current. Okay, so ohmmeter must have an internal source of voltage to create current necessary to operate the movement. Ohmmeter also have an appropriate ranging resistors to allow just the right amount of current. Three types of ohmmeter: series ohmmeter to measure high values of resistances, shunt ohmmeter to measure low values of resistances, and multi-range ohmmeter. This is simple ohmmeter. This is MMC. Black test lead and red test lead. This is black probe and this is red probe, the probe of the ohmmeter. Ohmmeter should have voltage supply to operate the meter. Okay, this is scale of series type ohmmeter where the right side of the scale is 0 ohm and the left side is infinite. Okay, I think the scale is incorrect because at the right must be the lowest. Okay, this one must be infinite. So the scale must be started with the lowest range and then increase the range until the highest range at the left side. I will take out this figure later. Okay, so when there is infinite ohm, meaning that at the left side of the scale, it is here. No continuity between test lead. Okay, we know that for open circuit, where no current flows through the circuit, so the resistance will be very high, or it can be said as infinite ohm. Okay, no continuity between test leads, zero current through the meter movement. The needle points toward the far left of the scale, meaning that here. Okay, voltage and current meters have zero at the left of their scale. Okay, if you look at this analog meter, for current and voltage measurement, the left side of the scale start at 0 and then the higher scale here at the right side. But for resistance, the lowest scale, okay, the lowest value of resistance is at the right side, okay, and the highest range at the left side. Opposite to current and voltage scale. Okay, this is for measure infinite ohm, where there is no resistor, but the probe of the ohmmeter is we did not touch the end of both end of the probe. Okay, so no continuity. This is where we want to measure 0 ohm, or we want to calibrate the ohmmeter. The test leads are directly shorted together like this. We short the red and black leads together, the meter movement will have a maximum amount of current through it. Okay, now no resistance, right? You can see there is no resistor be measured by this probe. Okay, so resistance is 0. So when R is 0, the current will be very high, maximum amount of current. So the needle will go to the right, okay, because here 0 ohm. Okay, understand or not? Any question? Any question? Any question?
No.
No.
Okay.
Tapi doktor dalam tingkat tu tak ada macam ni.
Sorry?
Dalam tingkat.
Apa dia Akif?
Dalam tingkat.
Tingkat ke?
Tak ada macam ni kan.
Maksud you meter ke?
Range dia.
Oh, range.
Tak ada kan?
No. Yeah. In Tinkercad, you just put the value of resistance that you want. Okay, very simple. Straightforward. Okay. So now this is simple ohmmeter with V equal to 9 volts. Okay. Bear in your mind that we need battery to operate the ohmmeter. Let's say V is equal to 9 volt and RM is internal resistance of the MMC. RM is equal to 500 ohm. Okay, current will be 18 milli. How to get 18 milli? How to get? Akmal Luqman? How to get 18 milli?
Yes, begin.
How to get 18 milli?
VIR.
VIR. How did you get 18 milli here?
V over R.
Okay, V over R. So, what is V? The value of V?
9.
9. R?
500.
500. So 9 over 500, we get 18 milli. Okay, which is far beyond the full scale rating of the movement. Okay, the IFSD. Okay, the current needed to operate PMMC here is 1 milliamp only. Okay, it is far. So 18 milli is far beyond 1 milli. So this is an excessive current. Such an excess of current will likely damage the meter. This is accomplished by adding a series resistor to the meter circuit. So we add series resistor to the circuit to compensate the excess of current. Okay, the observer movement is connected in series with a resistance R1. So R1 here meaning that resistance R here. Okay, so here. Aku apa Siti ni boleh? Boleh mas hujan tu kan? Hujan tu sebelah boleh tak tekan loceng rumah sebelah? 57. Balik dulu tu balik Sorry. Hmm, sorry. Okay. The observer movement is connected in series with a resistant R1 and a battery which is connected. Okay, so R1 here is series resistance here. Okay, so R1 is only a notation. Okay, sometimes it may represent as RS. Okay, so we understand that R1 is a series resistance. Okay, it may be RA, R, RS, okay, and a battery which is connected to a pair of terminal A and B. Okay, terminal A and B, meaning that the terminal that should a resistor be located, okay, here at terminal black and red. Okay. Across which the unknown resistance is connected. The current flowing through meter movements depends on the magnitude of the unknown resistance. Therefore, the meter deflection is directly proportional to the value of the unknown resistance. Okay. Now that the right value of R has been calculated, we are still left with a problem of meter range. Okay, now imagine that we want to design analog ohmmeter. Okay, we want to design. Okay, as our previous lecture, we design voltmeter and ammeter. So now we want to design an analog multimeter. So we know that at the right side here is 0 ohm. Okay, and at the left side here is infinite. So we want to know what is the value of R at the middle of the scale. Okay, you as an engineer want to mark the value of R at 25% of the scale, 75% of the scale, or maybe 80% of the scale. What is the R? Should be located at the scale. Okay. So ohmmeter is non-linear scale. Why non-linear scale? The scale of an ohmmeter does not smoothly progress from 0 to infinity as the needle sweeps from right to left. The scale starts out expanded at the right hand side with the successive or sequential resistance values growing closer and closer to each other toward the left side of the scale. Okay, we can see here this is 0 ohm. Okay, the scale at the right side is quite large. Okay, 0.5 here, 1, 2, 3, and then become closer and closer, smaller and smaller, right? 10 and then 20, 50 here. Okay, at the right side, the scale is quite large. I mean, understand what I mean? The scale is not linear. Okay, it's not linear. Understand or not? Class understand.
Yes.
Okay, so okay, now let's design analog multimeter. We want to design the scale at the analog ohmmeter. Okay, this is the circuit diagram of basic ohmmeter. We have PMMC here. RM is in internal resistance of PMMC. We have standard resistance or series resistance, or you can call it as R1. Okay, it is the additional R that needed to compensate the excessive current that I mentioned before. Okay, this is where we locate the R that we want to measure. We call it as Rx. Okay, resistance to be measured. A and B is probe of the meter. Okay, the red and the black leads. Okay, and we have battery. So this is series circuit actually. So if you want to find the IM is the current flow through the circuit. It is equal to the voltage. Okay, let's say we name it here as EB. This is battery. Okay, The voltage divided with the summation of Rx plus series resistance R1 plus Rm internal resistance of PMMC. So Rx is the resistance to be measured. Okay, so now the first step is to find what is the value of standard R here, R1 or Rs. Okay, R1 or I like to name it as Rs. R1 is the notation in the figure. Okay, so Rs or R1 here. Okay, please do not be confused. It's just a notation. So Rs or R1 the same. So Rs here is what? Okay, now at FSD. FSD is at full scale deflection. Full scale deflection meaning that we put the probe, okay, black and red together. We touch the both end of the probes together, meaning that there is no resistance or Rs is equal to 0. Okay, so when Rs is equal to 0, meaning that we short the both end of leads together. Okay, and then the needle will point to 0. So this is a full scale deflection. Rs is equal to 0. So here, let's say Im is equal to 1 milliamps. Okay, this is an example. Im is equal to 1 milli. Okay, Rm is given 100 ohm. We want to find Rs, the additional R that will compensate the excessive current, right? Okay, what is Rs? Rs is 0 ohm, no resistance. We short the both leads together. We short the probes together. Okay, so Rs is equal to Rs or R1 is equal to V over I, and then minus Rm minus Rx, right? Okay, so 3 divided with 1 milli current. Okay, minus 100 minus Rx. Rx is equal to 0. So now we get the value of Rs or R1 here. It is 2.9 kilo ohm. Understand or not? Understand or not? This is the first step. The first step is to find the value of Rs. This is the general procedure, okay? General procedure to design an analog ohmmeter. Any question? Can I understand or not? Understand or not?
Understand.
Okay. Understand. Okay. So, okay, now we get the value of Rs. Okay, and then you want to know what is the scale at the middle, meaning that half scale. Okay, half scale deflection, 0.5. Okay, at 0.5 full scale deflection, meaning that current is half. So Im is equal to 0.5 milli instead of what?
100 milli.
100.
1 milli.
1 milli lah.
Instead of 1 milli. So now, because the needle is pointed at the middle of the scale, we want to know what is the value of R should be marked here. Okay, current must be half. Okay, because current is full at 0 just now. Okay, so Im is equal to 0.5 milliamp. So now what is the value of Rx? R here. Okay, so now we want to know, let's say we take a resistor that we don't know its value. What is the value of resistor? But the needle must be marked at the middle. The needle must be marked at the middle of the scale. Okay, so now what is value of Rx? Rx is unknown resistance. Okay, so from this Ohm's law, okay, from this Ohm's law, R is equal to V over I. V is 3 divided with I. So I is 0.5 milli minus RS, RM 100 and minus RS is 2.9 K as we calculated previously. So now we know that RS is equal to 3 kilo ohms. Okay, so at the middle, RS is equal to 3 kilo ohm. Okay, if we refer to this figure, it seems like at the middle, the R here should be 4 ohm, right? Okay, but this is an example. Okay, this is an example. We do not know what is the value of RM. Okay, what is the value of RM for this analog meter? So this is an example only. Okay, so about 3 kilo ohm. So at the middle of the scale, the R here must be marked as 3 kilo ohm. And 3 kilo ohm is about RS, right? Our RS is equal to 2.9 K. So meaning that at the middle of the scale, okay, RS is approximately to RS, okay, because of the small value of RM 100 ohm is small value as compared to RS 2.9K, RS 3K. Okay, so relatively RM is small. Okay, so that RS is approximately to RS at the middle of the scale. Can you understand? Can you understand?
Can.
Okay, so now we want to conclude that for half scale deflection, Rx is the value that we want to measure, resistance that we want to measure. Rx is equal to Rs plus Rm. Okay, meaning that at half scale deflection, the unknown resistance will be the value of summation of R in this circuit. Okay, the summation of R in this circuit is Rs plus Rm, which is 3K. Okay, Rs is 2.9K, Rm is 100 ohm, Rs plus Rm is 3K ohm. Okay, so at half scale deflection, Rx is equal to R1 or Rs plus Rm or about Rs. Okay, so using Ohm's law a few more times, we can determine the test resistance value for a quarter and apa ni other scale deflection as well. Okay, so with the same procedure, you can find other scale. Okay, you can find what is the Rx or at 0.25 full scale deflection, meaning that here, what is the R should be marked at 75% of the full scale deflection, meaning that here, or other scale, maybe 80% here, 40% here, 20% here. Understand?
Yes.
Yeah.
Okay, good. Okay, so this is the conclusion. At half scale deflection, Rs is equal to R1 or Rs or Rs plus Rm. Okay, because of the small value of Rm, we approximate Rs to be R1. Okay, so we can prove the statement. Okay, by this example, the series ohmmeter in figure A is made up of a 1.5 volt battery, a 100 microamp meter, okay, IM, and R1 is RS, which makes R1 plus RM is equal to 15 kilo ohm, meaning that R1 plus RM is equal to 15 kilo ohm. Okay, battery is equal to 1.5, current flows through the circuit is equal to 100 microamp. Determine the instrument indication when RS is equal to 0. Okay, meaning that when RS is equal to 0, what is the value of the measurement, or where the needle should be placed. Okay, what the needle should indicate the value. Okay, IM, so we want to find IM. IM is equal to V over R. V is equal to 1.5 divided with summation of R. So RS is equal to 0, meaning that RS is equal to 0 here. 0 plus R1 plus RM is 15K. So meaning that at full scale deflection, where RS is equal to 0, the full current is equal to 100 microamps. Okay. So now where is the needle located, at the right side or at the left side on the scale? At the most right side or left side? Class? Class, where is the indication of the needle of the pointer of the meter? At the right side or at the left side?
Right.
Right.
Okay.
Right.
Okay.
That is right.
Because RS is equal to 0. Determine how the resistance scale should be marked at 0.5 full scale deflection, meaning that at the half scale deflection. Okay, so at the half scale deflection, current will be divided into 2. 100 micro divided into 2, meaning that it is half, 50 microamp. Okay, so we know that this is the equation of the circuit. So we want to know the RX. RS is equal to 1.5 divided with 50 micro minus, okay, R1 plus RM is 15K, so it is equal to 15K. So now it's proven where at half scale deflection of the meter. Okay, imagine we have analog meter. At half scale deflection where the needle points at the middle. So RX is the resistance to be measured. RS is equal to 15K. It is same as the value of R1 plus RM or RS plus RM. Okay. So for this ohmmeter with 1.5 volt battery and 100 microamp current, okay, when the needle points at the middle of the scale, we should mark that scale as 15K. Okay, so this is the explanation. You can read it. So when RS is equal to 0, current will be at full. When RS is equal to RS or summation of RS and RM, RS is R1. So current will be half. Okay. So the disadvantage of simple ohmmeter described previously is the decrease in voltage of internal battery with time and age, where the ohmmeter scale will lose accuracy. Okay. It may cause the full-scale deflection current drops and the meter may not reach 0 ohm when AB are shorted. They only function correctly when measuring resistance that is not being powered by a voltage or current source. Cannot measure resistance with an ohmmeter on a live circuit. Otherwise, the measurement is invalid. It is because the ohmmeter's accuracy indication depends on the only source of voltage being its internal battery. The presence of any voltage across the component to be measured will interfere with the ohmmeter's operation. If the voltage is large enough, it may even damage the ohmmeter. Okay, so the disadvantage of simple ohmmeter, as we learned previously, that the decrease in voltage of internal battery of the ohmmeter with time and age. Okay, so when the voltage is decreased, the full scale deflection will not point at 0 when AB are shorter. AB is the probe of the ohmmeter. It may not reach 0 ohm. Okay, it only can function correctly if there is no live circuit or the ohmmeter is not powered by a voltage or current source. Okay, this type of ohmmeter is never considered to be a precision instrument, but can be taken care of by an adjustable resistor R2 connector in parallel with the meter. So we add adjustable resistor. We call it SR2. Instead of this series circuit of ohmmeter, we add R2 in parallel with RM. Okay, where is RM? RM is here. We put R2 parallel with RM. Okay, so if we refer to the circuit, we put R2 here. R2 parallel to RM. Okay, R2 is variable resistor. So this is the symbol of variable resistor. We have resistor and we put the arrow like this. R1 current limiting resistance. Okay, R1 is RS to protect ohmmeter as we discussed earlier. R2 is the additional R that located parallel to RM. This is variable R or adjustable R for zero adjust resistance. Okay, the battery R and so on. RS is unknown. Okay, so the same step to mark zero reading, we short terminal A and B. So RS is equal to 0 ohm. Maximum current flows in the circuit. Okay, why? When R is infinite, so when R is equal to 0, I will be maximum. R2 is adjusted until the movement indicates full scale current since the resistance will be 0. Okay, so we short terminal A and B, meaning that there is no R. R is equal to 0. And then we adjust R2. We adjust R2 because R2 is adjustable resistor or variable resistor. We adjust R2 until the needle point at maximum. Okay, it is at the right side. At this time, the total circuit resistance is R1 plus R2 parallel with RM. R1 plus R2. Okay, this is a parallel circuit. Okay, so total circuit resistance is the R here. Okay, R here at terminal A and B. So Rm parallel with R2 and then we add with R1. R2 parallel with Rm and then we add with R1. Okay, the pointer will assign at 0 ohm. Each time the ohmmeter is used, terminals A and B. Okay, terminal A and B is the probe of the ohmmeter, the black and red leads. are first short-circuited. And R2 is adjusted for 0 ohm indication on the scale, meaning that the needle points at full scale. It is at the right side. If this procedure is followed, then even when the battery voltage falls below its initial level, the scale remains correct. Okay, how to mark infinite reading? Terminal A and B are open. Rs is equal to infinite. No current flows in the circuit. No deflection of the pointer, and the needle we go to infinity. Okay, so so now we want to know what is the value of R1 and R2. Okay, because this is design. So we want to know, we want to design the value of R1 and R2. The value of R1 and R2 can be determined from the value of Rx, okay, by using half full scale deflection method. Okay, so as we know that at half full scale deflection, as we learned previously, at half full scale deflection, Rx is equal to what? For simple series ohmmeter, Rs is equal to
R1.
R1.
RS
Okay.
plus RM.
Yes, okay. Rs is equal to Rs plus Rm, right? Okay. Meaning that at half full scale deflection, Rx is equal to the summation of R in the circuit, right? Okay, now for basic series ohmmeter, we have R1 and Rm. So at half full scale deflection, Rs is equal to other R, meaning that R1 plus Rm. Okay, it is the total R except for Rs, right? Okay, so the same concept for series ohmmeter with shunt resistor. Okay, with shunt resistor, meaning that this is shunt resistor, R2 is shunt resistor. Okay, so the same step, the same concept. So at half scale deflection, Rs is equal to the total R in the circuit, meaning that R2 parallel Rm and then plus with R1, right? R2 Rm divided with R2 plus Rm is R2 parallel with Rm. Okay, R2 parallel with Rm and then plus with R1. Okay, so this is half scale deflection method. Okay, so far can understand or not?
Yes.
Okay, good. Because I don't want to explain the derivation. Okay, actually, this slide show the derivation of R1 and R2. Okay, say Rs equal to R and so on, blah blah blah. Okay, and then derivation again, derivation until we get R2. And then we derive blah blah. This is Kirchhoff current law KCL, and then we get R2. Okay. Okay, but we know that it is high possibility to have final exam and test online final exam and test, right? Okay, so that you can refer to your notes. Okay, how to get R2, how to get R1. You can just use the final formula. Okay, you just use the formula of R2 and where's R1? So of R1. So these are the derivation only. The derivation, you can go through the derivation, but I just want you to know that full scale half full scale deflection method is where Rs is equal to R equivalent of the rest. Okay, meaning that R2 parallel Rm and then plus with R1. Okay. How to find R1? Use formula. How to find R2? Use formula. Okay, now if you understand the concept, we go to example 1. This is series ohmmeter with shunt resistor here. Okay, in the circle above, 1 milliamp meter movement. Okay, 1 milliamp flows here with an internal of 50 ohm. So 50 ohm here is represent which R?
RM.
Rm, good. Okay, so Rm 50 ohm, Im is 1 milliamp. The battery voltage is 3 volt here. Half scale deflection should be for 2.5K, meaning that, okay, at half scale deflection, the needle will point at the reading for the scale at half scale deflection is 2.5K. Okay, I think you can understand. The question is to find value of R1 and R2 with formula. B, find the change in the value of R2 if the battery voltage reduced by 10%. Okay, so we know that in this subtopic, we add R2 to compensate the decrease of voltage because of time and age, right? So if the battery voltage reduced by 10%, what is the value of R2? Okay, since R2 is the additional R, it is variable R to compensate the decrease in voltage, the battery. Okay, see what is the half scale deflection if battery voltage reduced by 10. Okay, so when the voltage, battery voltage reduced by 10%, what is the new scale at half scale deflection? Okay, so this is the information. Im is equal to 1 milli, Rm is equal to 50 ohm. Okay, so at half scale deflection, R is 2.5K here. Okay, calculate value of R1, or we call it as RS, or R2. So, based on this formula, R2 is the adjustable R. R1 here is the R here or RS. We can call it as RS. Okay, so please please be careful. Okay, maybe sometimes we put this R1 as RA. Okay, R2 here we name it as RY. Okay, so please be careful. Please be noticed that R2 in this formula is referred to variable R here. R1 is RS here. Okay, so R2 is, we use the formula IFSD, meaning that I am here, so 1 milli, this is 10 to the power of minus 3, meaning that 1 milli, okay, 1 milli, and then multiply with Rm, 50, multiply with RH. RH is the half full scale deflection of R, okay, it is 2.5K, divided with E. E is the voltage, battery voltage. 3, okay, and then minus I FSD again, meaning that minus 1 milli, okay, so 1 milli, and then multiply with RH. RH is equal to 2.5K, we get 250 ohm. So R2 here is 250 ohms. Okay, and then R1. R1 is equal to this formula. RH, okay, put the value of RH. And then minus Im or IFSD multiply with Rm and RH divided with 3. So R1 is equal to 2458.33 ohm. Okay. Any question? Just use the
No.
formula.
No, clear.
Okay. So B, find the change in the value of R2 if the battery voltage reduced by 10%. Okay, by 10% meaning that the new voltage is 0.9 of 3, right? Or 10% is 0.3 volts, so 3 minus 0.3 we get 2.7. So this is the new voltage. Okay, the new voltage after the decrease by 10%. So what is the value of R2? R2 will be the new value. Okay, put the new value of V, 2.7. Other parameter is remain. Other parameters are remain. So the new R2, because of the reduction of voltage of battery by 10%, R2 becomes 625. R2 should be changed from 250 to 625 ohm to compensate for this reduction in battery voltage. Okay, so the R2 is changed to 625 ohm. Okay, see what is the half scale deflection. Okay, now the half full scale deflection is changed because of the reduction in battery voltage. So what is the half scale? We want to know the new RH. We know that RH is equal to, okay, at half full scale deflection, Rx is equal to the equivalent R in the circuit, right? Okay, so RH is referred to Rx here. Okay, Rx is equal to RH. So R2 parallel with Rm and then plus with R1. Please substitute the new R2. Okay, the new R2 because of reduction in battery voltage. So now the new RH or the new resistance at half scale deflection is 2.505 kilo ohm instead of 2.5 kilo ohm. Okay, any question? Any question?
No.
Okay. Okay, the next example is similar to the previous 100 ohm basic movement, meaning the RM is to be used as an ohmmeter requiring a full scale deflection of 1 milliamp IM and internal battery voltage of 3 volts. A half scale deflection marking of 2 k ohm is desired. Okay, so at the half scale deflection, the needle points at 2 kilo ohm. Okay, 2 kilo ohm is the half scale deflection resistance. Calculate the value of R1 and R2. So just use the formula and the maximum value of R2 to compensate for a 5% drop in battery voltage, meaning that find R2 with the reduction of 5% in battery voltage. Okay, so the same step. Find R1 and R2, use the formula. Okay, R1, use the formula. And then R2, use the formula. So we found that R1 is equal to about 1.9 k ohm and R2 is equal to 200 ohm. Okay, please be observed that R2 is smaller as compared to R1, large smaller than R1. And then what is the value of R2? The battery is dropped for 5%. So 5% of 3 volt is 0.15 volts. So the new voltage is equal to 2.85 volts. Okay, so we have to find the new R2. Please substitute the new voltage and we will get R2. Any question? Any question?
No.
Okay. This is the last, I think the last two slides. Multi-range ohmmeter. The series type ohmmeter is only for a single range of resistance measurement. To measure resistance over a wide range of values, we need to extend the ohmmeter ranges. This type of ohmmeter is called a multi-range ohmmeter. Most suitable method, accurate reading, most widely used nowadays. Okay. This is a multi-range ohmmeter where we can select ranges. That's all for today. Okay, since last week we have learned many subtopic. Today only one subtopic. Okay, any question before we end our class? Any question? No question. Okay, how many of you today? 34. Next week we will have quiz one. Quiz one. LO1. Quiz 1 is for LO1. LO1 is chapter 1. So next week we will have quiz 1. It is on chapter 1, only 2%. 2% of the overall 100%. Okay? Any question before we end our session?
Okay, Doctor, next week on the Monday.
Sorry?
Next week the quiz will be on Monday or Friday.
Let's try on Monday. Not decided yet, but let's try on Monday. The medium is maybe you learn Microsoft Teams, not decided yet.
Okay, thank you.
Itu chapter 2 number 8. Apa? MT, any problem? Number 8. This is voltmeter. Okay, have you how many of you get 20 kilo ohm per volt?